Okay, so we resume our lectures on planning. This is the second lecture in the series of lectures on AI planning. Uh, what we intend to do today is to start with a quick recap of what we were doing in the last class. Namely, we were looking at what a planning problem entails and how we can use an algorithm to train an automated system into performing a planning task. So we are going to go a little bit deeper into that today with an example, the same example that we used in the last class. And in the next class we are going to look at a couple of other algorithms which uses slightly different approaches. So let's start by taking a quick recap of what we were doing in the last class, and then we can resume our discussion on the algorithms. So in our discussion we were looking at the partial order planning algorithm, and we referred to this algorithm as a partial order planning algorithm because the plan that it produces at the end is not a totally ordered plan in general. There could be actions which can be eventually executed in multiple different orders. So the plan actually produces an order between certain actions but leaves the other actions, some other sets of actions, to be potentially concurrent, in the sense that they can be executed in a chosen order of the designer. There are three important components towards understanding the partial order planning algorithm. Of course, the actions which are given to us, and also we have two very special actions. One is the start action, which gives us the initial world, and the finish action, which specifies the goal state. In addition, we have two types of artifacts: orderings and bindings. Orderings are sequence specified for actions. So when I want to indicate that a particular action A must be executed before B, then I put an ordering constraint from A to B. So the orderings are primarily defining constraints which force one action to be taken before another action. And bindings are important when your actions have variables and you need to instantiate those variables into certain constants or maybe with other variables, and only then you get the desired effect of the action. So we are going to look at orderings and bindings in the context of the example that we discussed in the last class, and through that we are going to understand how the algorithm for partial order planning works. So as you may recollect that we started off by defining the initial plan, and the plan will have, as was discussed in the last slide, the set of steps. Now these steps are the actions that form the part of the plan. The orderings, which tells us that in what order these actions need to be executed, and again remember that the orderings may not define a total order, it may define a partial order. And we will have bindings, and we will have a fourth type of constraint which are called links. So let's see how each of these are added as the algorithm proceeds. So we start with the same example where initially we are at home. So the start action that you see here, it has the consequence of at home sells BS book sells TST and sells TS biscuits. So these are the four consequences of the start action. So they are the effects of the start action, and they define the initial state and my initial state of knowledge as well. So my initial state is that I am at home and I know that there is some bookstore BS which sells books, there is some tea stall TS which sells tea, and there is some tea stall TS which sells biscuits. And we have the finish action which defines the goal state or the goal world, and in that target we have four different sub goals. I must have a book after the plan is executed, I must have tea, I must have biscuits, and I must be at home. Now you may wonder that at the start action we did not specifically say whether I have tea or not. Now by default, whenever there is nothing specified, we will assume that that predicate does not hold. So we will assume that in the initial state only those four predicates that are shown there, they are true. Have tea, have biscuits, these are not true. Have book is not true, because they are not explicitly specified in my initial state of knowledge. So anything which is not explicitly specified in a given state is assumed to be false. Now the start action obviously precedes the finish action, because that's where the plan starts and finish is the last step of the plan. So we can always add the ordering constraint which says S1 precedes S2, and S1 precedes S2 means that in this case the start action precedes the finish action. Now this is our initial state of the planning problem, and we also have two actions at our disposal which we have to use to construct the plan. These two actions are the action go Y, which, as we discussed in the last lecture, is an action which enables me to go to a destination Y when I am at a source X. So the precondition is I am at X, and the post condition or effect is that I am at Y, and obviously if I am at Y then I am not at X, and that is explicitly indicated here. And the second action is by X. For by X to be executed, I need to be at some place Y such that Y sells X, that is, it sells the product that I intend to buy. And on execution of this action by X, my effect is have X. So these are the two actions which are at my disposal. So now if we look at the partial order planning algorithm, it's an iterative algorithm. So it may have to try out different things, backtrack, fail, and then again retry. All these things are possible. So where you see this loop, that loop actually is the embodiment of this trial and error, and you can see the four steps that we do inside the loop. So the first step that you see here, okay, let me move into mode where I can do some inking on this. Just give me one moment, please. Right. Well, so let's see. In this algorithm, we are starting here with a minimal plan, which is our initial plan. Remember that initial plan only has the start and finish actions, and there is no other actions. Now in each iteration, it first checks here that whether the present partial plan that we have, whether that itself is a solution. Now what's a solution? A solution is one where all the sub goals are satisfied and there is no remaining sub goals in the plan for which we will need any further action. So that's when we say that the plan is a solution. So we check in each iteration whether we have already reached a solution. If we have not reached a solution, then there is some sub goal, which is still unfulfilled. So we still have to fulfill some sub goals. In that case, what I am going to do is I am going to select some sub goal from the plan which is not yet fulfilled, and then corresponding to that sub goal I will choose an operator which is an action. So I will choose an action, and after I have chosen the action and placed it in the plan, I will see whether the plan is executable, in the sense that sometimes, as we noted in the previous class, that after you have put in some actions you find that the steps of the plan cannot be executed in any order. So if we try it in one order, it destroys the preconditions of some other actions, and vice versa. So if we end up in that kind of a situation, we need to go back, maybe discard the chosen operator, go back and then again start at the beginning of the loop. So that's how it's going to proceed, by backtracking, retracing, etc. So now after you have seen this basic scheme of things, let me discard the inkings. We move into the first step, that is the step of selecting a sub goal. So what sub goal do we select? So pick a plan step S from steps plan where a precondition C has not been achieved. So let's look at this. So let's say that we start by choosing this have book, this one, as the sub goal which has not yet been fulfilled. There are others, by the way. So for example, this is also a sub goal which has not been fulfilled, this is also a sub goal, this is also a sub goal. These are pending sub goals. So we start with one of them. So let's say that we start with have book. Now the next step is to choose an operator by which we can fulfill that sub goal. So how do we choose that operator? So we choose a step S dash from the operators or the steps of the plan that has C as an effect. So we choose an action which can give me the sub goal. Now if there is no such step, if I find that there is no action which can give me that sub goal, then we fail here, which means that we need to go back and try other things. Otherwise, I will use that action, I will place that action in the plan, and because that action S dash creates the condition that I need, the sub goal that I need, so that action obviously has to precede the action S. So that's why we add the ordering constraint S dash precedes S into the set of orderings in the plan. And this is a causal link. So as you can see that I had some S which had an unfulfilled sub goal C. So now I place S dash as an action before it, and that gives me this C, and this and this link that you see from S to S dash, this is called a link. In this case, it's a causal link. It's a causal link because it causes the precondition C, which is the unfulfilled sub goal of S. So let's see with our running example what's happening here. So here, as you can see, that I chose the buy book as the action here. I chose buy book as my action. And why did I choose buy book? Because I can see in this description of the action here, that the buy book has a consequent have x, which you see here. Now because it has this consequent have x and my target sub goal was have book, remember that we had chosen have book to be fulfilled first. So I chose that action because it produces have of x as a consequent. Now here when you have this x here, this action actually has the consequent of have of x. Now this x is replaced by book here. So this is the binding. I am binding the variable x to book because I am interested in have book. So I will replace x with book. So now in my set of bindings I have added that this x corresponding to this action will be bound to book. It's like parameter passing to a function. It's like that you have a parameterized action, and because you want have book, you instantiate the parameter x to book, and that is the argument that is used here. So that's why in the precondition of this action by book, instead of having cells y x, which is what you had in the action definition, this x is also replaced by book because I have instantiated the variable x with book. So now I have this action in place. So now instead of having the original two steps S1 and S2, which was respectively start and finish, I now have three steps in my plan: start, then this buy book, and finish. Now what are the unfulfilled sub goals here? There are many unfulfilled sub goals. For example, here at y1 is unfulfilled, sales of y1 book is unfulfilled, then down here all these sub goals, have tea, have biscuits, have home, at home, these are all unfulfilled sub goals. So then in my algorithm I will now loop back and choose another unfulfilled sub goal and then put another action. So maybe in this way I put for the sub goal have tea, I put this action up here. For the sub goal have biscuits, I choose this action up here. And at home I am not addressing right now. So right now, after putting these steps, now I have 5 steps in my plan. There is some ordering between the steps. For example, there is an ordering which makes start precede every action, every step, finish succeeds every step, and in between these steps, like this one and this one and this one, there is no ordering between them. They are at this point of time partially ordered. So I am not imposing any sequence in which they should be executed. Right. Now let's see what happens next. So in next, it's not necessary that at every point of time I need to add a new action to fulfill some sub goal. Sometimes the sub goal can be fulfilled through binding. For example, let's go back to the previous slide once again. Here, sells y1 book, this one, was one unfulfilled sub goal. Now I see that if I instantiate y1, that is if I replace y1 by bs, then sells bs book is already there in my initial state, that is I have it here, I have cells BS book here. So then that can actually lead to a binding of this BS with this Y1 to give me cells BS book here. Okay, so that's what is happening here. So here the sub goal cells BS book is now fulfilled, and it is fulfilled because I bound the cells BS book, which is a consequent of the start, with this one. Similarly, I get cells TST and cells TS biscuits, etc. So in the algorithm, all these steps are added one after the other, and these bindings are carried out. Now if you see that right now my unfulfilled actions, my unfulfilled sub goals are which ones? I don't know how to get to this at BS yet, and similarly at TS is unfulfilled, and then this at TS is also unfulfilled, and at home is unfulfilled. So I have 4 sub goals still which are not fulfilled, so therefore the plan is not complete yet. But if you see, the plan already has 5 steps and a set of links which tells us in what way they may be executed. Then now we use the other action, that is go, if you remember correctly from the last lecture. So we put those actions in place now, and then at this point of time, as you remember, we still have to fulfill at y1 here and at y2 here. So far so good. We did not have any problems in terms of being able to execute this partial plan, because there is no dependencies between the different things that we are doing here, in the sense that we don't have a conflicting precedence between multiple actions. But then when we try to satisfy both of those sub goals with home, that is, in this case, if I replace y1, if I use the binding y1 to home, and I also bind y2 to home, then I have a problem. The problem that I have now is that they are not serializable anymore. That is, if I execute this one first, then it produces not at home, and if it produces not at home, then if I try to execute this later, then this at home is already destroyed, because it was destroyed when I executed go BS. It destroyed at home, as you can see here. On the other hand, if you try to execute this one first, we will have the same problem, because this too destroys at home and this one requires at home. So again we will have the same conflict. So what do we do here? So when we go into a step called resolve threats, the job of this procedure is to take the partial plan that we have and find out whether I am able to serialize the plan, that is, whether I can get a consistent plan out of the partial plan that we have. So how is it going to do it automatically? So let me explain. Let me remove the annotations. So we say that a particular, see what is mentioned here in the pseudocode is that for each S that threatens a link here. What does this mean? It means that there is an action Sj. To execute action Sj, I require some predicate C to hold as a precondition, there is some other action SI which produces as a consequent the C, and therefore the execution of SI enables the execution of Sj, because Sj needs C and Si produces C. That is, on execution of Si I am left in a world which satisfies C, and in that world I can execute Sj. Now if I have another action Sk which produces as a consequent, it produces, let's say, not of C, then I cannot execute Sk in between these two. For example, I cannot put Sk between Si and Sj, because if I did, then it will destroy the C and then Sj cannot execute because C does not hold anymore. So whenever I find such a pair, that is, whenever I find a pair where I have Si producing a precondition C which is essential for the execution of Sj, and I have another Sk which produces not of C as a consequent, then I will either execute Sk before Si or I will execute it after Sj. If I want to say that I will execute Sk before Si, then I will put a dotted edge like this to enforce that ordering. On the other hand, if I want Sk to execute after Sj, then instead of this one, let me get an eraser. Then instead of this one, we will put a different ordering action, namely this is going to force Sk to be executed after Sj. So in the pseudocode that you see here, the first thing that I drew is called promotion, because then I am taking this, I am actually taking this S double dash to precede Si, and in demotion I am adding S double dash to after Sj. Now the S dash that you see here is the name of the action, and the S double dash that you see here is the step, that is, the instantiation of this action into the plan is S double dash. But in a way you can think that both are the same. So just to avoid confusion, you can think that this is actually S double dash that we are talking about. But for theoretical correctness, the two are not exactly the same. One is the uninstantiated action, and the second one is the instantiated action, which is a step in the plan. Right. Now, after I do this, I still have to check whether the plan is then serializable, whether it is consistent or not. So let's see what's going to happen if we do it on this one. So now here you see I have what are my threads here. So if I look at this link, sorry, not that link. Yeah. If you look at this execution, the execution of this particular action. It requires at home. But then if I execute this action before this one, then it's going to destroy the at home. So therefore I say that, well, I should put a link like this, forcing this action to be executed after this one. But then in a similar vein, this action is also threatened by this one. So by a similar reasoning, I need to now put an ordering constraint like this. Now after you add these two ordering constraints, then your check for a consistency of the plan will fail, because now you have a cycle of dependencies. So if at any point of time, if you examine the links that are there in the partial plan, and you see that there is a cycle of links, and then that means that you are trying to impose an order, but that order itself has some conflicts in it, because if I take this one, then this is saying that it should precede this, but then if you take these two, then it says that this should precede this one. So you have a set of cyclic dependencies, which is therefore indicator that your plan is not consistent. So what the partial order planning algorithm does is that it looks at each and every link. Whenever you introduce a new action, it's going to see whether this action is going to threaten any of the existing links in your plan. If it does, then you try promoting it or you try demoting it. So this is a non-deterministic choice here that you see. I could either choose to promote it or I could choose to demote it. So I could either choose this or I could choose this. Actually what I will do is I will try out promotion, and then if the consistent plan is not obtained, that is if I return a failure, then I can go back and try the demotion. But if I try all possible promotions and demotions in all the existing edges and still there is no consistent plan, then I know that I need to go back and change some of the steps itself, because if I put that combination of steps, I will not get a plan, right? So that's what the resolve threats plan procedure helps us in evaluating. So in this way, by using the resolve threats, I will add this thing. Okay. So now, okay, so I just skipped one step here. So just let me go back here. So here what we found was that there is no way to execute it. So what do? We have, as I said, we have to go one step backwards. So what we do here in terms of going backwards is that we remove this link. We say that, okay, let me get rid of this link. So the step that I reach is here. Now I try to, previously what I had done was that I had instantiated y2 also with home, that is I did this. But now what I am going to do is I already found out that that's not going to work. So what I'll do therefore is that I will try to reach or instantiate y2 to something else, and when I backtrack and try that, then I will try replacing y2 with bs. Now if I replace y2 with bs, then I know that go bs has the effect of add bs. So add bs is a consequent of the go bs action. So now I know that therefore because this go BS produces the add BS, I can then do this after this. So if I do that, then I already have Y2 substituted by BS to get at BS here. At TS here, sorry. Because you need, I am messing things up. Just give me a moment. Let me erase and make a clean slate of it. Right. What happened here was that I instantiated Y2 to BS. So then Y2 is BS, and then from there I can go to the T stall to get to at TS. Okay. Now let's move on. Now after I have done this, is there anybody threatening anything? So we see yes, there is a threat still in this partial order plan. And what's the threat right now? The threat is that the buy book action needs add BS as the precondition, and the go TS action takes away at TS. So as you can see, here is my SI, here is my SJ, here this is my C, and this is my this action. I have lost my pen. This action is my S double dash. So I know that if I execute S double dash in between SI and SJ, then it's going to destroy the at BS, so therefore I will not be able to buy the book. So to prevent that, what we need to do is to either promote this or demote this. Now promoting this action is not possible because it is already after SI by virtue of this link. It is already after SI, so you cannot promote it, you cannot take it to above SI. But what you can do is you can push it to below SJ, which is the demotion. So in this case we demote it to come below SJ by putting this kind of an ordering constant. So that's what is done here. So let's go through the animations. Here I will do the demotion and put this link, and this red link prevents me from going to TS before buying the book. Now we are getting a feel of how the whole automated thing works by progressively adding these bindings, these links, and these orderings. And then similarly, you remember from the previous lecture that we can complete this plan. There are a few more ordering links that we need to put because they again threaten certain links, and then finally we get this plan. Now there is something that we have skipped here. The thing we have skipped here is that there can be partially instantiated operators. That is, operators where not all variables are replaced with constants. So should an operator that has, for example, the effect not at x be considered a threat to the condition at home, right? So I have some condition in some action. Let me see. I have some condition at home. Okay. It's a precondition of some action here, some Sj. and there is some SI which produces this, and then there is some action here. This one does not produce not at home, but it produces not at X. Okay, and at this point of time in the plan, we may have situations where this X is not instantiated to anything at all. And you may recall that in the previous class we alluded to something like this. For example, you may have a goal which says that I need to be at X and sells X, let's say coffee. So effectively my sub goal says that I need to be at some place which sells coffee, and it may so happen that in a particular point of the plan the X is not instantiated to anything, it's just uninstantiated at that point of time. Now at that point of time, are we going to treat this S dash, for example, the S dash here, to be a threat to this link? And the answer is yes, because later on we may replace, maybe we can use a binding before this action where X is replaced by home, and when that happens, then this is going to turn out to be a threat. So therefore we have to look at not only existing threats like we saw in the past, but also threats with partially instantiated actions, because they can potentially lead to threats later on when the variables get bound to something. So therefore we need to learn how to deal with these potential threats, and there are several ways in which we could do it. One option is that we bind X to something that resolves the threat. So we simply don't let it remain uninstantiated, we just bind it to some constant which is there in our dictionary. Or we resolve now with an inequality constraint. So instead of letting it be like as we saw here, that we allowed it to be not at X or at X, we kind of say that, well, it's fine to have not at X as long as X is not home. So we add a constraint that X not equal to home. So now what does that mean? That means in my action S double dash, which was the threatening action, previously we just had not at X, but now with that I am putting a conjunction with that, another predicate which says X not equal to home. Now if both of these are satisfied, then S does not threaten that link, because that link is threatened only if X is instantiated to home. So therefore in this case, adding this additional constraint, inequality constraint, resolves the threat. Or we could resolve later. So at this point of time we could choose to ignore the threats, and we could then carry it over and then resolve them later. And there are ways to do that resolving of constraints later on by using the constraint satisfaction technique. So either of these three could be used in a planner. Now, how does this change the definition of the choose operator? So we previously, when we are saying that we choose an operator which satisfies the sub goal, here what we want is that to have C dash as an effect, we need a step S from the set of operators such that I if I unify C with C dash, that is, okay, so let me draw something here that will make things clear. So here I have an Sj which requires a C as the precondition. Now I have some Si which produces C dash, right? Now see, this C dash is uninstantiated. Now, did we see something like this where the consequent is uninstantiated? Yes, we did see. Where did we see that? Let's go back here. Observe here. Let me remove the ink annotations. See here, I had this y1 which is uninstantiated, and then what I do is that when I use this action at some point of time, when I instantiate this y1 to home, at that point of time this becomes replaced by home, so then it becomes not at home. Now when I am doing this instantiation, I am actually unifying what is here and what is here. Okay, in a more generic sense, if you remember the unification of predicates, you could have a predicate px here and you could have a predicate say p with say g of y here. Then the unification of these will replace x with gy. Now that means that I am replacing x with again something which is not instantiated. So but that's what may happen. So let's go back here. Out here, that's what we are saying, that we are unifying C with C dash under the unify operator, and whatever you get as U is essentially the replaced thing, that is whatever you have achieved. Now what you do is you add U to the bindings of the plan and then you add the causal link like this. Now under the binding U, this C dash under the binding U, that is if I use U on this one, then I get C. Okay, so that's why it satisfies the precondition of Sj. So this is the step that we need to take whenever we are dealing with uninstantiated variables as the consequence and as the preconditions of plans. And similarly, when we want to resolve threats, there also we need to see whether the threat can happen under any binding. That is, remember that here the C and the C dash that you see here, the C dash and the C may not be exactly the same because one may not be instantiated fully, or maybe both are not instantiated fully. But if there is a binding under which they unify, then under that binding it may so happen that the link is being threatened by the new action, and in that case again we have to follow the steps of promotion and demotion. So all that was slightly on the heavier side, I suppose, to grasp at the first level, but I am sure that once you go over the algorithm in the book, and in the light of the discussion and the examples that we have done here, you should not have a problem in understanding how the thing is working. So that's the partial order planning algorithm, and we are going to do some exercises on partial order planning shortly. And in the next lecture we are going to look at a completely different type of algorithm, where we will build what is called a planning graph, and we will show how from the planning graph a plan can be extracted automatically. So that's it. Thank you very much.